The challenge with measuring the frequency response of microphones is that usually the microphone's frequency response is better than the source speaker used to play the test signal to measure it. This means you need to use measurement techniques that ensure you're measuring the microphone and not the speaker. SoundCheck offers two great ways to do this. The first is what we call the Equalized Speaker Method. First, we measure the source speaker with a calibrated reference omnidirectional microphone that has a flat frequency response. We apply the reciprocal as an equalization curve for the speaker, then measure the microphone under test, or DUD, in the same position as the reference mic. The second method is the substitution method. Here, we first measure the source speaker with a reference microphone, then the source speaker with a microphone under test in the same location. Then, we subtract the microphone under test result from the reference microphone result to show just the characteristics of our DUD. Let's take a look at these measurements. Pre-written sequences for both of these methods come with the SoundCheck installation, so we're going to use those today. I'll start with the Equalized Speaker Method. I'm using an SEM measurement microphone as my reference microphone, and I'm using the AmpConnect 621 audio interface because, as well as microphone inputs, it has an integrated amplifier to power my source speaker, a single driver, wide bandwidth, Cambridge audio mix. This makes it easier to position the microphones by pointing them at the center of the speaker. First, we need to equalize the speaker. We're going to use SoundCheck's built-in calibration sequence to do this. It plays our step sine signal, measures the frequency response. We have a few reflections here. We take the reciprocal of the response and equalize the output of the signal generator and measure again. You can hear it boost the low frequencies. Instead of it being plus or minus 20 dB, it's plus or minus 1 dB or less. Because the speaker is nonlinear, it will be slightly different at different levels, so we can equalize the equalization to further refine the EQ curve. Now, let's look at the calibration in the memory list. Here's our speaker, and we can see the EQ curve and the residual correction after the EQ. And you can also see the phase here. Now we're all calibrated. Let's make a measurement. We use a step sine sweep, play it through the speaker, capture the frequency response, calculate the sensitivity at 1 kHz, and display our results on a graph. We also have a couple of arbitrary limit steps here. You'd want to customize them based on your device. Here we go. Here you see the frequency response in phase. As you can see, it's fairly flat. And down here, we have a frequency response aligned to 0 dB at 1 kHz, which is a standard way of displaying microphone response. And we can see our mic sensitivity is about minus 5.5 dB volts per Pascal. Now, let's look at our alternative method, the microphone substitution method. In this method, rather than using an equalized speaker, we first play our step sine sweep and measure a calibrated reference microphone. We then substitute our microphone under test and measure again. Next, we subtract out the measurement of the reference microphone to get the raw response of our microphone under test. This removes the effect of the speaker's response on the measurement. We need to make sure we have the test microphone and reference microphone in the exact same position to minimize variance in the measurement. If we look at our test sequence, we can see that we have two acquisition steps, one for the reference mic and one for the mic under test, along with a curve division step using the division operation in linear mode. Let's run the sequence. It reminds me to make sure my reference mic is calibrated, which it is, and it prompts me to put it in front of the mouth simulator. Let's do that. We're using a source speaker instead, but you can use a mouth simulator if you prefer, as they both fulfill the same function. It's acquired the data. Now it's asking me to put the microphone under test in its place. I'll try to get it as close to the same spot as possible. Let's continue. And it's acquired the data, performed the division, and here's our response. This lower graph here shows the responses of the two microphones. The blue line is the reference mic, and the orange line is our mic under test. And this top graph here shows the normalized frequency response after the division. You can see the sensitivity at 1 kHz is minus 6 dB volts per Pascal. which aligns well with our first measurement using the equalized speaker measurement. So there you have it. 2 simple methods for measuring microphones that ensure any non-linearities in your speaker don't affect the measurement. And of course, these are some of the most basic microphone measurements that you can do in SoundCheck. We can also measure directional response, acoustic overload point, signal to noise ratio, embedded mics, MEMS mics, and more. If you have any questions or would like to see more microphone measurements, please get in touch with us. We'd be happy to demonstrate.